Okay. Okay, thank you everyone for joining us. Today we're very happy to have Anwesh of UBC, University of British Columbia, and it's going to speak about arithmetic statistics and Iwasawa.
Thank you, Payman, for the invitation, and I would like to thank all the organizers for this opportunity to speak at the Fields number 3 seminar. This is the first time I'm speaking at the Fields seminar, so I'm really looking forward to it. So my topic is arithmetic statistics in Iwasawa theory. So these are two big name terms which are not really seen together very often. So let me start by going over some of the basics in both of these subjects. So before continuing, I just want to mention that everything that I'll be talking about today is joined with Debanjana Kundu. So let me just recall a few facts from arithmetic statistics, which are very well known to the audience. So we'll be talking about the arithmetic statistics of elliptic curves. And of course, one of the most important invariants associated with elliptic curve is the rank of the model weight group. So essentially, arithmetic statistics has to do with the study of the average behavior of certain invariants. And these invariants will be associated to the model weight group. The main invariant that is studied is the rank of the elliptic curve. So for instance, the rank distribution conjecture states that 1/2 of elliptic curves are rank 0 and the other half of rank 1. So this is based on certain heuristics, Katz and Sarnock. In particular, this implies that 0% of elliptic curves are expected to have rank greater than or equal to 2. And of course, like I'll talk about what it means to for 1/2 of elliptic curves to have rank 0, 1/2 of the elliptic curves to have rank 1. Essentially, elliptic curves are ordered according to height. And but I will make that notion precise later in this talk. So I want to go over some very well-known results about rank distribution. And essentially, the idea goes back to Bhargava and Shankar, who studied the average size of certain Selmer groups. So essentially, one relates these Selmer groups to certain integral forms, and then studies the average size using techniques from the geometry of numbers and algebraic geometry. So here are some consequences. So we show that the average size of the 5 Selmer group is equal to 6. And as a result, they're able to show that the average rank of all elliptic curves is less than 0.885. So this average rank, of course, is conjectured to be equal to 0.5 because 1/2 of elliptic curves is supposed to have rank 0. The other half is supposed to have rank 1. They show that less than 20% of the elliptic curves have rank greater than or equal to 2. Once again, this is conjectured to be 0%. We show that at least 20% of elliptic curves have rank 0. Once again, this is conjectured to be exactly 50% of all elliptic curves. On the other hand, Iwasawa theory is based on a very different philosophy. And it is a study of certain Galois modules associated with elliptic curves. And so essentially, it's like a very Galois theoretic, the methods are very Galois theoretic. And these Galois modules also rise from Selmer groups. And the study of the structure of these Selmer groups is one of the main motivations of this subject. However, there's one key difference between the Selmer groups that we study in Iwasawa theory and the Selmer groups that Bhargava and Shankar study in arithmetic statistics. And the main difference is that in Iwasawa theory, one studies the Selmer groups defined over certain infinite towers of number fields. So this might sound like very complicated and unnatural, but it turns out that the behavior of these Selmer groups is the Selmer group's a lot more well-behaved over these infinite towers. And in some sense, you know, we have more techniques to study them over infinite towers than over like a given number field. And I want to sort of convince you that, you know, doing something like this actually gives rise to a lot of very rich and interesting mathematics. So let me briefly talk about the Galois representations associated with elliptic curves. I'm sure that what I'll talk about is very well known to the audience, but I want to set some notation. So that E be an elliptic curve defined over the rational numbers. So given a prime P, and the prime P is going to be fixed throughout this talk, and that's going to be one of the main themes of Iwasawa theory, is fix a prime P. So for fixed prime P, let E P the n be the P the n torsion subgroup of E of Q bar. So this is basically just as an abstract group, 2 copies of Z mod P the n, and it's also equipped with the action of the Galois group. So we want to construct some kind of linear algebraic object out of these modules, E P the n. So P is going to be fixed and n is going to vary. And the object that we want to consider is called the p-adic Tate module. So what we do is we observe that for every n, the multiplication by p map gives us a map from e p the n plus 1 to e p the n. So there's a natural map, which is multiplication by p. And with respect to these maps, we take the inverse limit. And this inverse limit is called the p-adic Tate module. Now it's an exercise in the theory of elliptic curves to show that this p-adic Tate module is just Zp plus Zp. So it's a free Zp module of rank 2. However, it's not just an abstract Zp module of rank 2. It's also equipped with an action of the absolute Galois group, the Galois group of Q bar over Q, where Q bar is the algebraic closure of Q. So the absolute Galois group, which is a very rich, it's very rich in structure, acts on this free Zp module of rank 2, and it gives rise to what's called a Galois representation for every prime P. And this is a non-abelian object, a non-abelian projection of this absolute Galois group. So for every pair, E and P, we get one such Galois representation. And here, GL2ZP is the automorphism group of this Tate module. So the Tate module is 2 copies of ZP. The automorphism group is therefore GL2ZP. And so we encode the action of this absolute Galois group on the Tate module via a homomorphism from the absolute Galois group to GL2ZP. And we get one such homomorphism for every pair, E comma P. Okay, so now we want to study 2 interrelated problems. And from the perspective of this talk, we're going to study questions in Iwasawa theory. However, if we consider the slide, we can study questions that arise naturally in the theory of Galois representations as well. And some of these questions are currently being studied by myself and Tom Weston, which are not directly related to Iwasawa theory. However, in this talk, we'll talk about Iwasawa theory only. So what we can do is we can fix an elliptic curve over Q and then vary all primes P. And then we get one Galois representation for each prime P. So we get rho EP for each prime P where E is fixed. And as P ranges over all primes, we can study certain invariants associated with these Galois representations. So we can sort of study the variation of such invariants. On the other hand, we can consider the dual problem, and this dual problem is sort of like more in line with, what people classically refer to as arithmetic statistics of elliptic curves, where elliptic curves are actually allowed to vary. So what we can do is we can fix a prime P and then study the average behavior of invariants associated to rho EP, where P is fixed. Now, E ranges over all elliptic curves, and these elliptic curves are going to be ordered according to height or conductor, just like in arithmetic statistics. So these are 2 interrelated problems that one can study. And this is the main theme of this talk. Okay, so now in order to sort of motivate Iwasawa theory, I mentioned that one studies Selmer groups over certain infinite extensions. However, one does not consider any arbitrary infinite extensions. It turns out that for many reasons, one wants to consider a very specific infinite extension called a ZP extension. And it's because, these ZP extensions will have some really favorable properties. So the canonical example of a ZP extension is called the cyclotomic ZP extension. In fact, there's going to be one for every number field. So let me go over the construction, which is relatively simple. So let's fix a prime number as always. So the prime number is P. And then for every natural number n, which is greater than or equal to 1, that Qn be a Z mod P(n) extension of Q. So this is a degree P(n) extension of Q, which is contained in the cyclotomic field generated by P(n) plus first roots of unity. There's a unique sub-extension of degree P(n), which we call Qn, and we have one for every natural number n. And we're going to set Q naught to be equal to Q. Okay, so then one can show that. So, given number field K, we're going to let Kn be the composite of K with Qn. Kn is called the nth layer in the cyclotomic ZP extension. Now one can show that basically these number fields indexed by n form a tower. So K is equal to K naught is contained in K2, is contained in K1 is contained in K2, etc. And this is called the cyclotomic tower. It's called the tower because it's an infinite extension. So you can think of these number fields sort of like lying on top of each other, and it's a tower. So it's called the ZP extension because of the following reason. One can take the union of all these number fields. And taking a union of these number fields, one gets an infinite extension of Q, which is Galois. And one can show that its Galois group is actually isomorphic to the p-adic integers. This is an exercise in infinite Galois theory. Turns out that the Galois group of Kn over K as constructed as Z mod P(n), and then one just gets an inverse limit of Z mod P(n), which is ZP, the p-adic integers. This is why it's called the ZP extension. So I want to talk about some early investigations conducted by Iwasawa, which sort of led to a lot of interest in this subject. So what Iwasawa did was, given number field K, he studied the variation of the P-class groups of Kn as n goes to infinity. So of course, P is fixed throughout. So just to make that more precise, consider the class group of Kn. So Kn is a number field. Its class group is a finite abelian group. We take the P primary part. And we just consider An of K, which is the P primary part of this class group. And so Iwasawa showed that there's a precise formula for the order of An of K for large values of n. So the order of An of K is basically a power of P. This power is expressed in terms of certain invariants. These invariants are called mu, lambda, and mu. And these are the Iwasawa invariants that we are going to study. At least we're going to study them in the context of elliptic curves. But they classically show up in this context for class groups. So as one can see, if this number mu, if the mu invariant is positive, then that means that the order of the class group increases very fast. So the question is, can one show that the mu invariant is actually equal to 0? So if the mu invariant is 0, that means that the order of these class groups will increase in a linear way in n. at least the power of p will increase in a linear way. So that's the question that that one wants to think about. However, we want to first touch upon Iwasawa's approach to sort of show that such a formula must exist. And I'm going to sort of make this a little bit more precise later in the talk. So for every natural number n, there is a norm map from en plus 1 to en. So these are, after all, class groups. There's a norm map relating these class groups, and one considers the inverse limit. So this is an inverse limit taken over all values of n. And it turns out that we want to think of this inverse limit as some kind of a, I mean, it's related to some kind of a Galois extension of k-sig itself. So there's actually like an action of the Galois group of k-sig over k. So this is ZP. So there's an action of this Galois group on this inverse limit. So this inverse limit a sig of k, it admits the action of ZP, which is this Galois group, but it's also a ZP module. So therefore, Iwasawa observed that such modules will actually be modules over a certain power series ring called the Iwasawa algebra. So the way in which he sort of introduced this ring was as follows. So for every n, one considers the group ring ZP of the Galois group of Kn over K. And he just considers the inverse limit of all of these group rings. And then he shows that this inverse limit, which is called lambda, the Iwasawa algebra, is isomorphic to, non-canonically isomorphic to a power series ring over ZP in one variable. So in other words, this inverse limit of class groups is a module over a power series ring in one variable, which is a really nice property. And the structure theory of ZP of x is fairly easy to understand. And therefore, in analyzing the structure theory of ZP of x in modules over ZP of x, one is actually able to define these invariants and prove the result of Iwasawa. And I'm going to sort of talk about this in a little bit more detail when we talk about elliptic curves. So the last thing I want to talk about with respect to number fields is the following: result of Ferrero and Washington. So Ferrero and Washington show that if K is an abelian extension of Q, so in other words, a number field extension of Q, whose Galois group, which is Galois, and whose Galois group is abelian. So for any such extension, the mu invariant must vanish for any prime. And the same is actually expected to hold for arbitrary number field extensions. Okay, so now we want to transition to Iwasawa theory of elliptic curves. And so the main idea here is to replace class groups with Selmer groups. So Selmer groups are not exactly analogs of class groups, because if I want to think of them in terms of Galois homology, they are defined by certain non-trivial local conditions. However, class groups are defined in a totally different way. However, there is some sort of analogy. And so the Iwasawa theory of elliptic curves was initiated by Mazur. And throughout, I want to talk about elliptic curves of a Q with good ordinary reduction in P. So unless I'm going to state otherwise, they're going to have good ordinary reduction. So what Mazur did was, so recall that Iwasawa studied the variation of class groups up the cyclotomic tower. Mazur studied the growth of the ranks of the elliptic curve of the cyclotomic tower. And so in doing so, he naturally started to study the variation of Selmer groups as one goes up the cyclotomic tower. So let me talk about Selmer groups very briefly. So the idea, so the key idea behind defining a Selmer group is to understand the model weight group in a Galois homological way. So it gives us some kind of a Galois homological description of the model weight group. So let me try and explain what that means more precisely. So EP infinity is the p primary torsion of the elliptic curve. So this consists of all p(n) torsion for all values n. Now the absolute Galois group acts on EP infinity. So EP infinity, in fact, is 2 copies of QP mod ZP with an action of this Galois group. So we define the P primary Selmer group as follows. So that F be a number field extension of Q. So the P primary Selmer group consists of certain Galois homology classes for the action of this Galois group on EP infinity. Now these Galois homology classes satisfy some local conditions. So in other words, at each decomposition group at every prime, there's going to be a local condition that these homology classes will have to satisfy. I'm not going to specify what those local conditions are in this talk. However, I can point out certain references for the definition of these local conditions. Essentially, the idea here is, the takeaway here is that the Selmer group actually sits in a short exact sequence. Sits in a short exact sequence. So on both sides of the short exact sequence, on one side, we have the P primary part of the model vector. On the other side, we have the P primary part of the Th-Rafferbich group. So now both of these groups on their own independently are very mysterious. So the model vector group is very mysterious. The Th-Rafferbich group is very mysterious. However, the Selmer group is sort of more amenable to study because it is given by some very explicit Galois homology classes with some very explicit local conditions. And therefore, it becomes possible to actually use tools from algebraic geometry and Galois homology and Galois theory to study the object in the middle, even though the 2 objects on either side are actually very mysterious. So this is really the main idea behind the Selmer group. It gives us it gives us more control over the model group in this way. Of course, there is also the Th-Rafferbich group that plays a role. So for instance, the Selmer group will be, so the Th-Rafferbich group is always expected to be finite. And the Selmer group will be infinite precisely when the model wave rank is greater than 1. So that's, for instance, one thing that one can observe from the short exact sequence. So just like we did with class groups, what we do is we just pass up the cyclotomic tower. So we have one Selmer group for every layer in the cyclotomic tower, and then we take a direct limit of these Selmer groups with respect to some very natural maps called restriction maps. And this is the pre-primary Selmer group over the cyclotomic extension. And this is the main object of study in the arithmetic, in the Iwasawa theory elliptic curves, Now, the point here is that the Galois group of K-sec over Q actually acts on the Selmer group. So this object also has some very rich structure. So what we want to do is we want to observe that the first thing that we observe about the Selmer group is that it's actually sort of a cofinite object. So it's not, it has no chance of being finitely generated over ZP. It's sort of cofinitely generated. So what one does is one considers the Pontryagin dual. And then when one takes the Pontryagin dual of the Selmer group, this is just a little bit of a technicality. Then it turns out that this is finitely generated and torsion over this Iwasawa algebra, which is ZP of X. So this is a very deep theorem of Kato that it's actually torsion. So we're going to call this object M6. And now we can introduce the Iwasawa invariants that we are interested in this talk. So as a ZP of X module, M6 decomposes into cyclic modules. It's torsion, so it's a direct sum of these cyclic modules. This actually follows from the structure theory of ZP of X modules. Now, I should mention here that it's not on the nose isomorphic to a direct sum of cyclic modules. You can think of various modules over ZP of X which aren't. However, it is isomorphic to this direct sum up to what's called pseudo-isomorphism. So up to a certain finite kernel and co-kernel, there's actually like a decomposition like this. So now in this cyclic decomposition, sometimes we're quotienting out by powers of p, and sometimes we're quotienting out by fg of x, where fg of x is a monic polynomial whose non-leading coefficients are divisible by p. So there's a decomposition like this, which is not unique, but the invariants associated to this decomposition are sort of well defined. So what one does here is one adds up the powers of p, and once we add up the powers of p, we can get the mu invariant. So this sum is equal to the mu invariant, and the lambda invariant is just the sum of degrees of these distinguished polynomials. So there's another way of the more implicit way of sort of defining these invariants, but I just want to point out that the lambda invariant is nothing but the ZP rank of M-sig. Okay, so I want to sort of start talking about the arithmetic statistics for these invariants. But first, let me touch upon this very well-known conjecture of Greenberg in the subject, which is completely open. So EP is a two-dimensional FP vector space with the Galois action. Now, if it is irreducible as a Galois module, then it is conjectured that the mu invariant is equal to 0. Now, this tells us a lot about what to expect for the mu invariants. Suppose we fix an elliptic curve of Q, which does not have complex multiplication, and we vary all primes P. Then it follows from Serre's open image theorem that EP is irreducible as a Galois module for all but finitely many primes. So this condition is satisfied for all but finitely many primes when you fix an elliptic curve without CM. So therefore, one would expect that the mu invariant will vanish for all but finitely many primes. Actually, more is known. So if E is semi-stable, then it's actually irreducible for all primes strictly greater than 11. And finally, if you want to consider the dual problem where we fix a prime P and vary the elliptic curve. So given a fixed prime P, Will Duke showed that EP is irreducible as a Galois module for 100% of elliptic curves. So now we are fixing the prime P and varying the elliptic curve, and now EP is irreducible for 100% of elliptic curves. So this sort of shows that the mu invariant should actually vanish like most of the time in whatever sense that most of the time means. So for a fixed prime P, it should vanish for 100% of elliptic curves. For a fixed elliptic curve, it should vanish for all but finitely many primes. So these are all, these results all are conditional on Greenberg's conjecture. So now the question is, what about the lambda invariant? So one can show that the lambda invariant is always greater than or equal to the model Weyl rank. And so we want to basically model the behavior of both the mu and lambda invariants in two cases. When E is fixed and P varies first, and then the more conventional question in arithmetic statistics, when P is fixed and E varies over all elliptic curves over Q. So we consider the following results of Greenberg. So suppose we have an elliptic curve over Q and its model Weyl rank is 0. Then for 100% of the primes of good order reduction, the mu and lambda invariants are both 0. And the Selmer group is actually 0 on the nose. So this is a result of Greenberg, which is known a long time ago. And one can also extend this result to the supersingular case. So suppose we have an elliptic curve with the same condition, the rank is 0. Then for all but finitely many primes of supersingular reduction, one can prove the same result. The mu and lambda invariance is 0, and the Selmer group is 0 on the nose. Now, one observes that there's basically like a slight difference. And the point is that there's actually like a sum in plus and minus on all of these terms. So what does this refer to? So when we have a prime of supersingular reduction, the Selmer group is no longer a torsion module. So it's not so easy to work with. However, what one does, so what is the convention in Iwasawa theory, is to study certain quotients of the Selmer group. So one introduces more strict conditions at P, local conditions, and one gets two different quotients of the Selmer group called the plus and minus quotients. And these quotients are actually torsion, and the mu invariants and lambda invariants are basically associated with these quotients. So we have the analogous result. So in the rest of the talk, I will not be touching on these plus and minus Selmer groups. I just wanted to indicate that one can prove results in the supersingular case as well in the slide. And I just want to sort of give a heuristic for what should happen when the rank is positive. So these results are all known when the rank is 0. I want to give a heuristic for what happens when rank is positive. So I want to introduce an object called the characteristic. So let gamma denote the Galbert group of Q6 over Q. Now, as you mentioned before, this Galbert group acts on this Selmer group. So what one can do is one considers the gamma invariants. So the subgroup of the Selmer group, which are left fixed by gamma. And then one can also consider the gamma coinvariants. So this is the quotient which is left fixed by gamma. And since the group on the right-hand side is a quotient, there's a natural map from the left to the right. It just takes an element in the Selmer group to its residue class in the quotient. And this map is called phi. Now, conjecturally, both of these groups are supposed to have ZP co-rank equal to the rank of the model wave group. So the generalized or truncated Euler characteristic is the order of the kernel divided by the order of the co-kernel. Now this need not be, so these orders need not be finite always, but they are finite whenever the rank is either 0 or 1. And there's actually an explicit condition for this, for the kernel and co-kernel to be finite, which I will not get into, but essentially we are only more or less interested in the cases when the rank is 0 or 1, because it's conjectured that 100% of elliptic curves have rank either 0 or 1. So we're going to assume that this number is always well defined. And so why are we introducing this quantity? The point is that this truncated Euler characteristic is related to these mu and lambda invariants, these Iwasawa invariants. And so this is a theorem of mine from a previous paper with Sujata, where we actually studied the effect of congruences on Euler characteristics. But I'm not going to talk about that in this talk. The essential idea is that the Euler characteristic is an integer. It's the power of p, but it's also an integer. And the Euler characteristic is equal to 1 if and only if the mu invariant is 0 and the lambda invariant is equal to the model wave rank. So this actually gives us a way to relate this Euler characteristic with the Iwasawa invariants. And this is the main, this is related to what's called the p-adic p-adic conjecture that we'll introduce, but this is basically the main tool used to sort of study these invariants on average, to sort of study the problem, to try and study how often the Euler characteristic is equal to 1 on average. So what is the goal behind this relationship? The idea is that there is an explicit formula for the Euler characteristic due to Pereru and Schneider. So assume that the T-Traffic group, the p-primary part of it is finite, which is a very standard assumption. We also assume that the regulator is non-zero. I'll talk about that briefly later. So under some very natural assumptions, the Euler characteristic exhibits a formula, which looks a lot like the BSD formula, but it's a p-adic version, which is why it's called it's related to, it's called a p-adic BSD. So I just want to touch upon what these terms actually mean in this formula. So here RP refers to what's called a p-adic regulator. It's basically a p-adic analog of the usual regulator. So there's a p-adic analog of of the height pairing for elliptic curves over Q. And the p-adic regulator is nothing but the determinant of this height pairing. So when I divide this p-adic regulator by p to the power of the rank, this is basically a power of p, a non-negative power of p. It's called this quantity here is called the normalized p-adic regulator. SHA E over Q is the Th-Rafferich group, which we're familiar with from the previous slides. At a prime L not equal to P of bad reduction, CL of V is the Tamagawa number. This is an invariant associated to the Kodaira, which tells us a lot about the Kodaira type of elliptic curve. E of FP is the number, so E of FP is the group of FP valued points on the reduction of E. And so this formula is actually an explicit formula for this Euler characteristic. And so the idea is to sort of study how often these terms in the formula are actually units, p-adic units. So that's the main idea. So I want to introduce some shorthand notation here. So the normalized regulator is going to be called REP. So just the p primary part of the regulator. SHA EP is going to be the p primary part of the Th-Rafferich group. Tau EP is going to be the p primary part of the Tamagawa product. And finally, alpha EP is going to be the p primary part of the group E of FP. So essentially what I'm doing here is I'm just using some shorthand notation for all these terms so that it's a little bit more convenient to work with. And we're sort of not very interested in, we're just taking out the p primary part. So we're sort of throwing away the p-adic unit because we're not exactly interested in, what that p-adic unit is. We just want to understand if when this is equal to 1 or not. So, so now the idea is that if all these four terms are equal to 1, then the Euler characteristic is equal to 1, and then we have this generic situation where the mean range is 0 and the lambda range is equal to the rank. So we want to basically study how often these invariants are equal to 1. So now let me just pause for a moment, and let's just go back to this formula, and let's just look at it. So the Th-Rafferich group is assumed to be finite. So this is like an integer. Its p primary part is going to be 1 for all but finitely many primes because it's an integer. This is also an integer, so its p primary part is going to be 1 for all but finitely many primes. So now we look at this term, E tilde of FP, and it is a theorem that this term is actually equal to 1 for 100% of the primes. So the only term that sort of causes a problem is a regulator, which is the first term in the p-adic BSD formula. So one would expect that the mean range should be 0 and the lambda range should be equal to the rank for 100% of the primes. And this is precisely the case when the regulator is equal to 1 for 100% of the primes. So computational evidence shows that this is to be expected. So for instance, one can look at a lot of primes and one will find very few examples where the regulator is actually not a p-adic unit. I think of this as some kind of an elliptic curve analog of the question of finding B-Frick primes. So B-Frick primes are very rare, but one doesn't know whether there are infinitely many of them or if they're 0% of the primes are B-Frick primes, etc. So this p-adic regulator being equal to 1 is a very sort of related question. And I mean, I'm not going to justify exactly why I think of these two questions as related, but there are some reasons. So this allows us to make a conjecture. So this conjecture is, recall that this conjecture is true when the rank of the elliptic curve is equal to 0. So if I have a fixed elliptic curve of a Q, then for 100% of the primes, the mu invariant is 0 and the lambda invariant is equal to the rank. And this conjecture is true precisely when the p-adic regulator is a unit for 0%, for 100% of the primes. So now we want to move on to talking about the dual problem, where the prime p is fixed and the elliptic curve varies over all elliptic curves defined over Q. So we fix a prime p, and then I want to now make precise what it means for the elliptic curve to vary. So we're going to assume, we're going to like consider elliptic curves which are non-CM. And associated to such an elliptic curve, we have a Weierstrass equation given by y squared equals x cubed plus ax plus b, where a and b are integers. And then this equation can be, one can find such an equation which is minimal in the following sense. The GCD of a cube and b square is not divisible by 12 power. So one has one such equation for every elliptic curve. And the point here is that this is the reason why one considers elliptic curves over Q, because elliptic curves over Q have this very nice property, that there is this minimal Weierstrass equation. So essentially the idea is that we're sort of thinking of elliptic curves as being parameterized by pairs of integers. So we're thinking of them as like points in a lattice. So now we want to talk about the size of elliptic curves. So like some elliptic curves are sort of have larger size than the others. This actually gives us a way to count the elliptic curves. So the size is basically called the height in this situation. One can also order the elliptic curves according to conductor. But in this, it just becomes a little bit more convenient for us to order them according to height. So we take the absolute value of a cubed and b squared and take the maximum of them. So a and b are the coefficients of the Weierstrass equation. So given a positive number, real number x, let E of x be the set of all elliptic curves of height strictly less than x. So if you want to think of elliptic curves as lattice points, you know, this is basically going to be a certain region in space. And as x increases, this region also increases. And the number of lattice points also increases. So once again, recall that we fix a prime p. It becomes convenient to fix a prime p greater than 5. So let EP of x be the subset of all elliptic curves for which are not very generic in the following sense. The rank is 0. The elliptic curves have good order reduction at p. And finally, the mu invariant is positive or the lambda invariant is positive. So recall that the generic case is when the mu invariant and the lambda invariant were both equal to 0. However, we want to consider the ones which are exceptional. So either the mu invariant is positive or the lambda invariant is positive. So we want to get some kind of upper bound for the density, the upper density of EP of x inside E of x. So what we do is we take the lim sub as x goes to infinity of EP of x over E of x and get some kind of an upper bound for it. So once again, let me just go back a few slides. And so the essential idea once again is one wants to study how often this Euler characteristic is equal to 1. So one wants to study how often all of these terms in the numerator are equal to our p-adic units. And when the elliptic curve has rank 0, the regulator is actually trivial. So this term here is trivial. And then one must study how often these three terms in the numerator are p-adic units. So then this is where one gets the expression on the right-hand side of the term. So there are three terms. Each one of them are contributions from the three terms in the numerator that we were looking at. So let me just explain what these terms mean. So F naught of P is a proportion of elliptic curves of rank 0 for which P divides the order of the Tate-Sharp for each group. So we do not have unconditional upper bounds for F naught of P. However, there's like so Cohen and Lenstra developed heuristics for the variation of class groups, and Delaunay extended these heuristics to the variation of Tate-Sharp for each groups. And these heuristics are very robust. And the exact prediction for this density is given by this number. So it's 1 over P plus 1 over P cubed, and then there's some kind of an alternating sum, there's some kind of some pluses and minuses, but essentially the order is pretty much like 1 over P plus 1 over P cubed. So essentially the idea is that this proportion is sort of like going to become smaller and smaller as P becomes larger and larger. And so they actually rapidly decrease. But this is only assuming Cohen-Lenstra heuristics. This is not an unconditional statement. So that was the first term in the above formula. And then zeta P minus 1, this term actually arises from the analysis of the Tamagawa numbers and how often, so each Kodara type has gives some restrictions on the model wave equations, and we kind of study those restrictions. And then putting all those conditions together and the restrictions together, we get a total of zeta P minus 1. Actually, a number much smaller than zeta P minus 1, but just to give a nice formula, we have zeta P minus 1 as a contribution from those Tamagawa numbers. And finally, the last term is the contribution of E of FP. So here I just want to explain what that term dP is. So dP is the number of pairs in FP cross FP such that the discriminant is non-zero, and the associated the associated Weierstrass model has a point of order P over FP. So there are a total of P square tuples AB, and so dP is the number of pairs for which there is a point of order P over FP. So dP over P square is some ratio which is smaller than 1. And this value dP is actually related to certain class numbers associated to certain forms called the Kronecker class number. But one can actually compute this using Sage. So one can compute these values using Sage. And we see that in general, the values of dP over P square actually decrease as P increases. But there's actually a lot of oscillation in this data. So let's just look at this data for a little bit. So initially, these values are still all very small. They're all smaller than 0.1. But initially at 7, the value is like 0.08. And then it goes down, and then it comes up again. It goes down, comes up again. It goes down for a while. It goes down, comes up again randomly. But then as one just looks down this table, one sees that the values are like approaching 0.01, which are like much smaller than the values in the beginning. So it turns out that one can, computing more values, it seems like the value should go to 0. So the question is like, what exactly should one expect for dP over P square? The point here is that this number is related to the number of points on the modular curve x1 of P over FP. And Niels Brunn was telling me that there are some papers about the variation of the genus of these curves, and over FP, and then the point counts of these curves. And there are some issues related to the models for these curves. I feel like I'm still not 100%. I don't think I understand the topic well enough to sort of come up with some kind of conclusive heuristic for what dP over P square should be, but at least computationally, it seems to be like going to 0. But I just want to say that the question is related to, model J curves over finite fields and how they vary. To modular curves over finite fields and how they vary. Sorry, how x1 of P varies. Sorry. So now I just want to talk about some more recent work. where we prove some lower bounds for these densities. So recall that this term is an upper bound for the density of exceptional curves. And now we want to talk about some lower bounds. So we want to talk about elliptic curves for which the lambda invariant is actually very large. So recall that this lambda invariant gives us an upper bound for the rank of the elliptic curve over Qn as n goes to infinity. So it gives us this kind of upper bound all the way up the cyclotomic tower. On the other hand, the model V rank of the elliptic curve over Q is expected to be sort of bounded. So this lambda invariant, on the other hand, one wants to study if this lambda invariant also is bounded or not, as one considers all elliptic curves defined over Q. And Greenberg showed that mu plus lambda can be arbitrarily large. So given a prime P, the mu invariant plus the lambda invariant can be arbitrarily large. So this is a classical result of Greenberg. But one wants to sort of understand if it can be arbitrarily large for positive proportional primes, for instance, and what exactly that proportion is going to be equal to. So, there's some lower bounds as follows. So let's fix a prime number P greater than equal to 5 as always, and let's fix a natural number n. So one wants to consider all elliptic curves of a Q for which mu plus lambda is greater than equal to n at that given prime. So Greenberg showed that, well, there will be at least one elliptic curve with mu plus lambda greater than equal to n. However, what we show is that there is an explicit lower bound, which is positive, for the density of such elliptic curves, which mu plus lambda is greater than equal to n. And this explicit bound involving both P and N involves certain infinite sums, but it's still very explicit. So it's a very complicated expression involving some infinite sums, but this quantity actually becomes smaller and smaller as n increases and P increases as well. So it's sort of giving this sort of very explicit result. And of course, throughout, we assume the finiteness of Shah in our arguments. So now I want to point out that, the question is, can the lambda invariant be arbitrarily large? Now, Greenberg's conjecture implies that the mu invariant should be 0 for 100% of elliptic curves. So therefore, assuming Greenberg's conjecture, this statement, mu plus lambda greater than to n, can be replaced by lambda greater than to n. So even though the rank of elliptic curves is supposed to be bounded, the lambda invariant, which is an Iwasawa theoretic analog, can be arbitrarily large, and it is larger than or equal to n for a positive density set of elliptic curves. So I want to touch upon some recent work. So the methods that we use in this paper are fairly robust. It can be generalized in various contexts. So for instance, with Hatley and Lay, we studied analogous question for anti-cyclotomic ZP extensions. So these are certain ZP extensions of imaginary quadratic fields. And now we can also study the question where an analogous question where the imaginary quadratic field is actually allowed to vary over an infinite collection of imaginary quadratic fields, assuming that the elliptic curve is defined over Q. And we prove a number of results about the variation of all these questions when the imaginary quadratic field is also allowed to vary. And we get some better results in that case. In fact, sometimes the Selmer groups that we consider in this paper are not even torsion. So then I also want to talk about some recent work with Bayanish and Kundu, in which we basically use these ideas related to all the characteristics to study the arithmetic statistics of rank jumps and growth of Selmer groups in certain Z mod PZ extensions. So essentially, the idea here is that one can fix an elliptic curve of a Q and just look at all Z mod PZ extensions of Q. And so that's an infinite collection. However, one can order them according to conductor. And essentially, one can study how often there's actually an increase in the rank of the model weight group. And one can also study how often there's an increase in the growth in the K-Shaft-Ridge group. One can also study how often there's an increase in the order of the Selmer group. One can also study these questions for a fixed Z-mod p-z extension and varying elliptic curve. So I mean, so in this paper, we study a number of these questions in the case when the elliptic curve is rank 0. And in a forthcoming work paper of mine, I will be proving like much stronger results about Z-mod p-z extensions and the variation of Selmer groups on average, the jumps of Selmer groups on average, and Diophantine stability. But maybe that is a topic for another talk. All right, so that is all that I want to talk about today. Thank you so much.
Well, thank you, Anwesh. Okay, are there any questions? I can't see anything in the chat box, but if anyone has any questions, you can just unmute yourself and ask, or you can just put it in the chat box, whichever you prefer. Okay, if not, we'll thank Anwesh again for a very nice talk, very clear. I think you gave us a lot to think about, Anwesh. Thank you.
Thank you so much.
We'll thank you. Thank you.